So as we move forward, it is going to be important to identify a carbon that is chiral. We've already seen that chiral carbons have a plane of symmetry around that molecule. There's an easier way to determine if a carbon is chiral or not, and it meets these two criteria that are listed on the slide, and it must meet both of them. So first, for a carbon atom to be chiral, it must be tetrahedral. So what that means, it must be bonded to 4 substituents and have 4 single bonds. If a carbon is only bonded to 3 substituents, it's not tetrahedral. It is trigonal planar, and one of those bonds is a double bond. If a carbon is only bonded to 2 substituents, and there's a triple bond, it is not tetrahedral, it's linear. So the first criteria is that carbon must have 4 single bonds, so that means it's tetrahedral. The second criteria, which must also be met, is that there are 4 different groups attached to it. And the key here is groups. It doesn't say atoms, it says groups. So on this slide on the left, we have an example of a chiral carbon because this carbon is bonded to 4 different groups, not atoms. So one of the groups is a hydrogen atom, the other group is a hydroxyl. So this carbon's bonded to hydrogen, then OH, and then the other 2 groups are both carbon-containing groups, but they are different groups because one of them is a methyl and the other is an ethyl. So if we look at the mirror image of this molecule, we see that if we superimpose it, if we take this carbon and, for example, take the image carbon on the original so that the 2 yellows are in the same place and so the 2 hydrogens are in the same place. The hydroxyl of the image will be where the ethyl is on the original, and the ethyl of the image will be where the hydroxyl is of the original, and no turning either of them around, just like no turning around the hands, will make it superimposable. So this is just to show you we're not going to be looking at a mirror image of every molecule as we move forward. We are just going to identify a carbon as chiral or not. 1, if it has 4 bonds, and 2, if each of those substituents are different. Now on the right we have an achiral carbon, and the reason it's achiral is that it has 2 of the same substituents, 2 hydrogens. So it is tetrahedral, but because it has 2 hydrogens directly bonded to it, it cannot be chiral. So let's take a minute and take a look at this chemical right here. 1, 2, 3, 4, 1, 2, 2-butanol, and identify which carbons are chiral and which carbons are achiral. So looking at the structure, we know that the end carbons are going to be achiral because they each have 3 hydrogens. This is the 3 carbon is achiral, so 1, 4, and 3 are all achiral because they don't have 4 different substituents bonded to them. However, the 2 carbon is chiral. It has a methyl group bonded to it on the right of the structure. It has an ethyl group bonded to it on the left. It has a hydroxyl group and a hydrogen. So there is a chiral carbon in 2-butanol, and it's the 2 carbon.